Yes. Actually, normally, you know, so small. The Muslims land yes, because the Muslims educated probably. I have simple people. But you can check maybe assignment 1 to 3. Actually, I need the school. I need I send for you today. Yeah, maybe share it in the group and share it. You can check the mistakes and yes, so I said because I did the I send the fee. He didn't schedule one. Yeah, maybe I really talking that because I need to completely decide you already emails on that they would be. Yeah, but at least I don't get a keyboard. Yeah, but one my I like that second. And you that's like the house. Just to get the junior was to be that. It's like how you mess with awesome. No, I have about 25. Maybe mine. No? I yeah. don't need to be relevant like after 2 years. Because it but in the end, yeah, it's right. No, I think they just you managed to make a decision. That's very interesting. Really interesting.
Hello. The guests are coming back, so maybe we need to wait for. They just come back.
Well, sorry, if there's a bit of an issue with lunch. But we can start. All right. We MC.
Oh, yeah, MC. Okay. Joe's not here.
So I go through diagnostic. Goes with the master student talk.
Oh, the message is okay. Okay, sure, sure.
That's it. But I'm talking to
Okay, afternoon, everyone. Very sorry for the slight delay. We continue our joint campus seminar by our Yankee Seng from the Malaysia campus. Title 2 Diagrammatic Categorifications.
First of all, I would like to apologize that I can't be with you in the morning because I have a class to finish. Yeah. So today I'm trying to work something. Research maybe all the things that are for this year, but maybe only when NYP or master students I could think about these things because most of the time we're teaching. So let's talk about some categorification, in particular some diagrammatic categorification. Actually, this talk is like a sequel talk. In this campus, I have talked about similar topic 2 times ago, but from different perspective. Okay, since today we have some people doing geometry analysis here, so I would like to talk from a viewpoint of symplectic geometry. But definitely, what I do is representation here. Okay. So let's talk about some interesting objects. At the capital E here, labeled by some M and W, be the lunar fibers, singularity of type AN. I will define what is this. Okay, so to define this, first of all, we'll define another thing called capital H. So let's show this capital H. So these are basically some n+1 tuple, complex tuple, that satisfies some algebraic equation. Okay, algebraic equation look like this: x0 squared plus x1 squared 2xn minus 1 squared plus some perturbation here. Okay, let's call it little h. Okay. So what's this leader h here? So this leader h will be some n plus 1 degree polynomials. Okay, it's n, so you decrease the degree. So what do I want this polynomial to do? Is I need to make sure that the zero set of this polynomial contain n plus 1 point. Okay, so this is the
Why?
the m here. Okay. So far, so good. And so if if you recognize this part, the first part of this sum, and if I evaluate h value at n equals n, let's say a negative value, then this is just a C. It's just some sphere. Okay. Cool. So yes.
Yes, then this one.
The cardinality of the set. This is for the zero set. So we choose these coefficients. The zero set of this S.
Por ejemplo, Lucas.
Huh? As long as you intersect with the zero, wait, anything. So, what do you have?
Lucas, for example, y cube, y
Cube. Like you mean something like this? Okay, let me draw. Be something like this?
Yeah.
Yeah, then so the zero set should be just one. Yeah. Wait, is it correct? Let me think. Not really, right? I think it's the whole thing, right? It's infinite, right? I guess it's infinite because okay, depend on how you want. Okay, well, so what's this? Like, can you give me the formula y minus x squared, something like that? No, not like that. I think it's x cubed. X cubed minus x squared equals 0, something like that.
Yeah. Oh, it's equal.
Simple. Okay. Okay. So this is a discrete set. Right? It's a discrete set. It's a discrete set. Okay. I mean, like,
That's like a fundamental of theorem of boundary. So n plus 1 degree.
okay. So this is not mirror fiber yet. Okay. Yes.
Are you counting, for example, loops, but that's counting multiplication, not counting multiplication.
Yes. So we like to be we like to be
Singles or singles.
Yeah, without multiplicity, yes. Okay. Cool. Okay. So from here, right? From here, we could define a disk. Okay. From here, we define a disk. This special disk here. We symplectic this, but then we just need a topological structure here. So for this set of coefficient, then basically we pick this coefficient quite small. Okay, so small enough. How small is it? Okay, we want it to be small enough to have this kind of properties here. So such that we get a compact, convex subset. So we really want something like a punctured disk. Okay, something like a. We want it to be compact, convex, and subset, such that this here. So this all the point that satisfy the length of this z, the length of z is less than equals to 1. So the nice thing about this is there's a closed bow, not closed, but a bow of radius 1/3 will be in there. And then your set of 0 will be inside here. Okay, and then it's contained in a radius of 2 bow, like that. Okay, if I wanted to draw this, maybe I can draw it here, maybe radius 2. And then your DW maybe can look a bit exotic, but compare convex. Then your D2 of 1/3, something somewhere inside here. And then all your 0 point will lie inside this hole here. Okay. Basically, topologically, we want this to be a punctured. Later, we're going to define something using this. So far. Of course, this requires proof, but then we'll hide the detail for now. It's very technical. Okay. So then we'll define this. Okay. So we'll define the unit fiber, the intersection of that HW with a closed bore of 1, radius 2. So usually we don't consider the whole fiber, but just a closed venecine fiber to the origin. Okay, and this thing is a symplectic manifold. Partly why they interested in symplectic manifold is because nowadays theoretical physics are really interested in symplectic geometry because it's captured, for example, it captures position and momentum together. A position and momentum form a symplectic manifold. Okay, with certain symplectic form that we don't really care in this talk. Okay, then since we have symplectic manifold, right? So in symplectic geometry, something very interested object to study is the Lagrangian. Okay, Lagrangian. So here we also define some interesting Lagrangian here. So we'll let C be a curve in the disk that we defined just now. Okay, with some punctured point. Let me include it in. Then we could define something called the Lagrangian sphere. Okay, so we will define Lagrangian sphere using level curve, kind of level curve. So let's call it LWC here. So this Lagrangian is depend on the curve, and then depend on your parameter W. Okay, that give you distinct root. Okay, so let's give some level curve here, or level surface, or depend on which dimension we're in. Okay, so let's define this. Well, so what is it? So just now I told you that if I fix some HWZ, right, I can get some sort of sphere. Okay, this is exactly what I wanted to do. Okay, so I could take the square root of the negative of the HWZ. Okay, if I fix the Z, I evaluate HW here. Okay, I get a value. If it is negative, I can make it positive by moving to the other side. Then I found a sphere there. And I will combine all these spheres together to build a higher dimensional field. Correct or not? If I have a dot, circle, put together, I will form a S2. Okay, and then this is exactly what happens here. Well, maybe I should tell you what kind of curve that I considering here. I can draw it for you so that you know what am I doing here. Yeah, let me finish this. Okay, so so just now we had something like a punctured this, right? DW. Okay, so this curve should be connecting two punches here. But then connecting punches means what? The endpoint, if you evaluate it, you should get like 0, right? Right. Okay, so what is like, for example, x1 squared plus x2 squared equals 0? What's that solution set? It has to be 0, just one point, because sum of positive number, if you want to get a 0, there's no way other than being 0. And then other than that, your HWZ should be like increasing in some sort. So the radius should be non-zero, right? Okay. So if you put these circles together, yeah, you form some sort of sphere. Right, this is the Lagrangian sphere. The nice thing about this Lagrangian sphere is the dimension is half dimension of the symplectic method. Yeah, this required proof, of course. All right, so we talk about our main objects here. So what do we do with this Lagrangian sphere? Well, because I'm representation theorist, right? So we care about algebra. So we'll define something called the Floer cohomology here. Okay. So Floer cohomology on two Lagrangian. Okay, two Lagrangian here. So a kernel of something divided by an image of something. So I need to tell you what's the differential here. Okay, so what's the differential here? Well, to tell you the differential, I even need to tell you what's the chain complex, right? So what's the chain complex? So let's write down the chain complex. I mean the chain group inside my chain complex. Okay, so what is it? The chain group is easy to study here. Okay, so basically these are just Z02 coefficient generating the intersection between two Lagrangian. Okay, so you take two Lagrangian, look at their intersection, and then count up to mod 2. Okay, mod 2 is important here to make sure that the differential works. Okay, yeah. Well, so what's this map here? So I take the intersection, okay, and then I'll count it with some multiplicity. That and we'll count with some multiplicity with the other points. Okay, so how do we count this? Well, this one is a very technical stuff from symplectic geometry. So again, we'll count this non-zero coefficient if this term here is non-zero mod 2. Okay, so I'm gonna tell you what is M again. And then I'll tell you why I'm cautioning by R. So M here should be some moduli space. Okay, so let me tell you what moduli space is this. So we're counting some moduli space. Maybe this definition looks a bit technical, but I'll tell you what is it really doing. So first of all, you have a strip. You have a strip, and then you place it in your middle fiber. Okay, obviously this strip has to be depending on my L0, L1. This is the section, right? So let's see how it depends. So first of all, it has to be satisfying the pseudo-holomorphic condition here. Okay, a bit like a Cauchy-Riemann equation. Okay, but then you don't always have the complex structure. So you only have almost. But that's the technicality you don't need to worry about for now. Just give you some idea. What are the conditions that restrict us to counting this? The other thing is, if you look around the boundary, on one side, it should be one of the Lagrangian, and the other side should be the other Lagrangian. Does that make sense? Okay, and then the two intersections should lie in the intersection. Okay, and then plus some condition from function analysis, like some Fredholm index condition, to make sure some linearization works. Okay, I can draw you some picture on this. So for example, let's think about a Lagrangian as a curve. It's easier to draw. Let's say L0 like this, L1 like this, right? Okay. So your U is some strip, maybe one side is L1, the other side is L0. Okay. Okay. Maybe such that at the intersection, one of them is X, one of them is X plus. Okay, so this we cannot simply count. It has to be recalled because to go satisfy the almost complex Cauchy-Riemann equation. Okay, so you need to count this, and then this space here is invariant under then we count how many of them. Okay. So that action of R, I think okay. So from here, what we are really interested is something called the category of Lagrangian, or sometimes we call it Fukaya category. Okay, so the object is what we have introduced. Maybe I already shrink down a lot of them, but for our purpose, that's okay. So these are the Lagrangian submanifolds. If you think of this Lagrangian sphere is enough. And the morphism here are the Floer cohomology. Okay, the HF L1 0. Okay. Okay, so there's a nice thing about this Floer cohomology here. Since we mentioned it as a cohomology, right? So that means there's a algebra structure there. We can multiply. Okay, so how do we multiply here? So here's how we multiply them. Well, again, we take HF L1, L2, for example, and HF of L0, L1. Okay, so something we can get is HF of L0 and L2. So meaning we send some intersection point here, two intersection point here to another intersection point with some multiplicity. Okay, so what's this map again? So how do we count it? Again, we have pseudo homomorphic. In this time, maybe we'll say it's a triangle, okay, because involving three vertices. With some, obviously, some similar pseudo holomorphic condition like what we had just now. I can draw a picture for you. Basically, just now we just consider the intersection of two Lagrangian, right? So this time round, maybe you can consider like that. Okay. So like X, Y, Z, like that. Like if you have a pseudo-homomorphic triangle that bounds them, then I'll count this. Okay? If you cannot find this, then your product should be 0. So yeah, go to the other vertex. Okay, so far so good. Surprisingly, okay, surprisingly, if you look at the big direct sum of the LILJ that I considered just now, and then look at the algebra, this gives a very simple description by some zigzag algebra that we call zigzag algebra. Or for in this case, we call it a type A zigzag algebra. Okay. So this zigzag algebra is very easy to describe. First of all, it is a path algebra. Okay, path algebra of this graph here. This graph is very simple. They just have adjacent, X, B2, balancing okay, degree of the vertex is always true other than the first sentence. Very easy. So you can compose them like path. Okay, maybe I can label their name. So for example, the constant path, we could call it E1, E2, E3, right? And then the path that join 1 and 2, we could call it 1 to 2, like that. Yeah. So for example, maybe I give another name in case I need it. So let's say 1 to 2 composed with 2 to 1 is a path that go around, right? Like this. Okay. We'll call it x1, for example. Okay, this path are what we consider most because I'm portioning out this half algebra by this relation here. Okay, if you go 2 steps away, then you'll be 0. And another condition is if I go to the left or go to the right, they should be the same. Okay, so all the loops are the same. So I kill a lot of things inside this matrix. So I just start with length 1 path and length 2 path. Yeah, so you think of this isomorphism here, which floor homology is related to xi, related to this constant path related to the left round. In fact, it's very easy to form this bijection, but maybe showing is a bit technical. So, for example, I write this. This could be corresponding to length 1 path, for example. And then a hash f of L1 and L1 will be corresponding to, can I draw this? Yeah, to something that generated by, let's say, E1 and X1. Yeah, something like that. I think, or maybe I should put a 1. No, just 1. Okay. Yeah. So what am I suggesting in this mapping here is, if you look at the flow homology of Lagrangian sphere, intersect with itself. So it's just the sphere itself, right? But then if you perturb that a bit, really what you get is I mean like, okay, so the flow homology of a sphere actually is a homology of a sphere. That's what I mean. Yeah, so we recover the homology of the sphere. So homology of sphere, you have the degree 0 term and the highest degree. Okay, are we done yet? Not yet. Okay, right. So there comes to my stuff. Okay, there comes to my stuff here. Well, so how these things are put together then? Okay, so again, let W can be the set of things such that we have the distinct root. Okay, so this is how we mentioned that it has a distinct root. That means our HW doesn't have singular point. Okay, so if you know a bit of singularity theory, right? This is exactly like how we avoid the singular. What do you mean? The what do you call that? To avoid the singularity. Yeah. Okay. One way to do it is you blow up. Okay. The other way, we could do deformation. This is exactly what we do. We perturb the coefficient a little bit. Okay. Yeah. So that the 0 don't stay together. Yeah. Okay. Then you can play around with this set of W here, meaning you look at the pi 1 of this W. So it turns out that pi 1 of this W is some break group. So this is a break group. Group, hide a break group. For those who are not familiar with break group, maybe you can think of SN. You can think of SN. So what is SN? So SN was XI, so generated by reflections, right? Generated by order 2 elements. Okay, so they commute. Okay, they commute if they are far apart. Okay, if they are far apart, they could commute. They are order 2 elements. They commute if they are far apart by some ij far apart, and then they break. Okay, they break if they differ by 1. Okay, depend on your bijection. But then break group is the one that you remove this order 2 condition. Okay, then that makes this group infinite. Okay. So this has apparently has an action on our Lagrangian category, or we can upgrade it to if you know a derived category version of it. Why? Because this break group here, this pi1w here, actually has an action on EW. So you can upgrade to the Lagrangian. Just look at the Lagrangian, how they change. And then if you know the Lagrangian, how they change, because then you know the category how change, then you can upgrade to derived category because you invert all the so-called fuzzy isomorphism. If not, never mind. You just think about how we change stuff in Lagrangian. Okay. So yeah. So the point here is why I want to talk about this dB here, because this dB has a relation with the dB category of the AN mod. AN. Okay. I told you what is AN. Okay, I told you what is AM, but I haven't told you the category yet. Okay, so the AM that appears here is exactly this AM that we mentioned. It's a path algebra that portion out degree 2 part, and then some loop condition in there. Okay, so let's tell you what's the category. So to tell you a category, I just need to tell you what's the objects and the morphism. Okay, so what's the objects? So the object is here is very simple. Okay, so I will define it as Pi. Okay, and you just take your algebra and then dot with your what we call an idempotent here. But then this is also the constant path that we see just now. A constant path is an idempotent because if you do it twice, you just say that. Right? Okay, it's an idempotent. This is a very general construction in the representation of representation theory of algebra. You need to look for the idempotent to split up your algebra. It's like a vector, it's like a basis, kind of like a basis. Okay. What are the morphism could occur here? Okay, so for example, maybe I can let you think a little bit. Right. So what should you think of this kind of here? So HM is think of a bunch of parts that should end with the constant part I. So you come from anywhere and then you stop at there. But you don't really come from very far, right? Because I already worn out degree 2. So at most maybe you come from I plus 1, or you come from I minus 1. Then from I and then go back to I. Okay, so these are morphisms we consider. So this one end with I, this one end with I plus 1. So what's the path that joins I to I plus 1? That's it. So if it is I minus 1, then it is I minus 1. Okay, so depend where you finish. So how about EI, or PI and PI? So you end with I here, and then you need to go to somewhere. But either you stay as EI, or you can make a loop and then come back to EI. So you should think of this as something called Yeah. So very nice thing about this, why I get along with this project is, this has actually a topological interpretation. It turns out that there's a nice topological interpretation here. Okay. So most calculation that I did before was exactly on that DW stuff. Okay. And you have a curve that connects these punctures. Okay. So maybe you have some curve like this. So how we assign, how we relate this PI to this curve is, you could draw a vertical line between these punctures, okay, and then label it like 1, 2, 3 in order. So whenever you see an intersection, right, you will place a P1 or PI there. You will place a PI there. So here is PI, here's PI, here's P2. Okay, so let's say there are number 1 curve and number 2 curve, right? Okay, so number 1 curve, we will call it PI. Since this is a trend complex category, right? Maybe we will put it like this if you are more comfortable. And the second one, we will have P1 and P2. Okay, but then how do we connect it? Okay, so we connect it like a counterclockwise way. Okay, so meaning counterclockwise around the puncture is surround. So in this case here is P1 to P2. So what's the map? I can put, there's only one choice. I put 1, 2 here. Okay, and then that's it. Okay, so nice thing about this construction is you can see that when the curve get longer, right, you can imagine this shape of it. Okay, how to make the curve longer? Can you imagine how I can get them? You can play around with action. This is one of the things you can do. Okay, so for example, I can, I could, wait, I could, I could commute these two. Right, depend on which direction you commute. Maybe let's do counterclockwise. Okay, let's do counterclockwise. So this picture will like extending this. Okay, so you will get extended. So then you will come back to this point. Make sense? Is it making sense? Okay. So in topology, this is not important. You just think of twisting it. Okay, so we can kind of elongate this curve and then changing the endpoint, right? We commute the point. But then what is this curve then? Okay, so let's see what this curve will transform into. So you got a P1, you got a P2, you actually got 2 P3, right? Correct or not? You intersect the third line twice. Okay, so what's the map I'm gonna put here? So following the clockwise, anti-clockwise position around punctured. So P1 to P2 is 1, 2, P2 to P3. Okay, so you can see that this I should go backward because it's a, sorry, am I right? Yeah. So you have to be counterclockwise around punctured. Okay, so meaning P3 here have to go to P2. So I will put this P3 here at the bottom. Okay, go to P2. Okay, and then how about this part here? So you need to go around the puncture counterclockwise. So P3 is coming down to that P3. Okay, so I'll put this P3 here. Okay, so we have to fix a convention, which is counterclockwise around puncture. So here is, we will say this loop thing will be S3. Okay, but the path will be just 3, 2 like that. So this is the Chang complex. If you don't like this, I can put it horizontal. Yeah. Meaning, how should I write it better? So I should write it as a matrix, right? So that it's a 2 times 1, so you go to 2 things. Similarly, I can do matrix here. I think I write the wrong direction, right? So this is 1 times 2, so I should put like this, 0x3. And for this one, I should, if I write as a matrix form, I should get 1, 2, and then 3, 2, like that. Yeah. Okay.
So you can check that this is actually satisfying the differential condition. Okay, if you try to compose this two map, you get 0. Because you got a length 3 path joining, length 2 path joining with this, and 1 path to get length 3.
You get length 2 path, then you get 0. Okay. So far, so good. Yeah, okay. So a nice theorem from Cohomology idea is this action here. So let me write down first before that. So let me write down the break group action for you. So then there exists a faithful type AM break group action on this category here. Okay, you don't care about DB is fine. Just think about this chain complex category. It's given by some bimodule complex. Bimodule complex. So this bimodule complex look like this. Star IP go to AM. And then its inverse, just change the position. Okay, so I introduce a new notation here. Notice that I place the I at a different spot, exactly because I put the constant path at a different spot. So meaning,
If I can put PI in this path and I put IP in this.
but this is a bimodule complex because from the left and right, you have a half algebra action here. Okay. Yeah. So let me finish about their story. Okay. So faithfulness. Faithful meaning there's an injective map from here into the map from this the group action is injective. Okay, this is what the faithful means. Yeah, because sometimes you could imagine that when you have a group action, right? Even if your group element is not identity, you could get an identity action. So this is not faithful. Okay, faithful meaning only identity element can give you that your set is something. So if you have a non-identity element, it definitely have to permute your set in some way. Okay, this is why is this important? Because back to the time they have some representation for break group, but it's not faithful. For example, the Dural representation is not faithful. But turns out that this is possible. Why? Because our category is actually graded. Okay, although we go back to the same object, but actually it moves up in a different level already. So that's the key point here. Use grading to differentiate the same element. Yes. Okay. So for example, these two P3, right? They should be in different gradings. Yeah, it should be graded here. So for example, I will grade it like this. Like if you graded by path length, for example, it's possible. Yeah. So although it's the same P3, right, but it's not really the same with grading. Okay. Yes. Yeah. So you could imagine that, or I twist it in somewhere, you come back with the same curve, but then you already shifted your chain complex to different grade. Either shift in this grading that we introduced, or you shift to the cohomology. Yeah, so there are at least two grading you can see here. Okay, so other than this, so why people are asking about faithful break group is because if you just look at this term here, look at that weird pi tensor IP here. Actually, you can prove that there's a functor isomorphism. Okay, functor isomorphism that looks like this. Okay, ui plus 1, ui isomorphic to ui, and then ui minus 1, ui is isomorphic to ui again, and ui squared isomorphic to ui plus ui. So your square become 2 times ui, sort of. And then uj should be 0 if I think I and j should be far apart. Okay, so if you say with not theory before, this is a very famous, very similar to templating. Okay, this is how the John found the John form. Okay. Why I said similar but not the same, because of this. For temporary algebra, this should commute exactly like the relation that I show you in symmetry group. So in this sense, sometimes you call this a new categorification of temporary algebra because of this. Because these two are isomorphic, it's very true. They're isomorphic to 0 before they are 0. Yes. 5 minutes. Okay. But suddenly,
Yes, like 5 seconds.
Can. Okay, finish soon. Okay, so this give a functor realization of temporary algebra anyway. Okay, but then because of this new categorification, we can't really get a nice invariant of not from here. Okay. If you recall how Van John get it is once he get this algebra, right? What he do is he take the trace. He take the trace of the element. Then that trace of the element will be the polynomial. Okay, so meaning I have to take the trace of these, I mean some trace operation of these bimodules. Okay, trace, yeah. Okay, so well, from this project, we did 2 directions. Okay, one direction that I did in a PhD with my friend Edmund, he's in Sydney now, was we changed the picture of this type A here to a type B thinking diagram. Okay, so meaning it's the same graph, but we have extra weight here. Okay, and then extra weight here will imply that there's some different relation between these two dots. There's different relation. We prove a faithfulness result there as well. And then we also have a topological meaning there, okay, which is by kind of reflection along this punctured disk. Okay, so there's a reflection, there's a disk. So there's a disk from this type A here, we kind of like reflected. So there's a Z mod 2 action here. Because even if you see on this thinking diagram, right? This type A thinking diagram and type B thinking diagram here, you can actually think of it as a folding. Okay, as a folding. Let me see. Where should I fold? Maybe I fold around here. Yeah. Okay, so there's a Z mod 2 action that we introduced there. Okay, so this is one of the direction we did. So because this story I started with symplectic geometry, right? I hope that our type B, so-called the type B Zigzag algebra, also have some description on Lagrangian there, for example. How to find this? Okay. Yeah. Second direction was 1 more minute, is it? Okay. So another direction is because in this story, right, we just only look at the one curve at one time. We just commute and then see how this curve changes. What if we consider multiple curve at one time? Okay, what if we consider multiple curve at one time? Something like that. Okay, see how this curve changes together. Okay, we suspect or we conjecture that if we able to work this out, we could get the real transform. But this is very computational heavy. Yeah. So for this, right, maybe I can tell you what the object is. Instead of just one m here, right, maybe we need to consider a multiple m here, am here, maybe n of them, with some rich product with xn. And so this is the category that we need to deal with if we want to consider multiple curves. And then this category, right, is really related to the Heisenberg category. So the endomorphism of the Heisenberg category is this one. Maybe to give you some ideas what's the technicality you would expect. Maybe my master student is here. Maybe I can just randomly say something so that he got some idea. So if you know about Heisenberg category, the basis there is like index by partition. How many? Okay. Index by partition. Okay. So you should have some partition, something like this. Okay, maybe something like this. Partition. Okay. And am I good like this? Okay, not very good. Maybe something like this. So this partition will define something called the Young idempotent. Is it Young idempotent? Yeah, there's some idempotent you can define from here. I think it's called Young idempotent if I'm not mistaken. Yeah, yes, yeah. Okay, good. Thank you. Yeah, we got the algebra expert. Okay, Young idempotent. Then we can draw some string diagram between them. Like you can connect them, right? Because this idempotent is like sum of permutation, something like that. Blah blah blah. Okay, maybe I'm not too accurate, but to give you some idea. But then this permutation, right, you should imagine as a string diagram. 1 to 2, 2 to 3, 3 to 4, 4 to 1, like that. Okay. So, but this is a sum of them, right? But then you are interested in the homomorphism space between, for example, these two things. Okay. So we are trying to figure out what's the basis. Okay, maybe I could stop here.
Some questions will speak. No, then let's thank you again.
Okay, thank you. Thank you.
So we only include bit depends on rules and we have a if we start, we start one half break, then we start,